This is a presentation on the law of large numbers. So first, just a quick introduction to the law of large numbers. The definition of the theorem is that the average of the results of repeating trials will be closer and closer to the expected value the more trials there will be. For example, let's say there are 10 trials of coin flips with 10 coin flips each. We would find the average for each trial for heads. Then we would average the 10 trials different averages, and then the result should be extremely close to the true average. This means that if the trials had 4 heads or 6 heads, this would average out to 5 heads. And one quote that gives an example of how each patron is a trial is from Naked Statistics, Stripping the Dread from the Data, from 2014, and this is page 79. And it states, the law of large numbers explains why casinos always make money in the long run. And this basically means that some would win big and others would win absolutely nothing. But since the average winning is less than what the casino usually receives, the casino would end up making a profit from the average of all of the patrons. Some important notations that we should keep in mind are that each trial would most likely be written as x. So for each trial, that means it'd be x1, x2, all the way to x sub n. And n is the number of trials. To find the average of all the means, you would add all the means together and divide it by the n number of trials. And this means that the average of all the means would be x bar, with the bar on top of the x. And the variance mean of the means is also found in an extremely similar way. There's more on this in the later slides. So there's no set limit to how many trials is necessary to be performed for the average of the trials. The only caveat is that the more trials there are, the more accurate the average of the means would be. So for the purpose of our class, weak and strong laws of large numbers could be used to prove convergence. But it normally has more to do with calculus. Weak notes that there is a convergence of probability in the expected value, but strong means sure convergence. More about this is found later in the slides. Uniform law of large numbers is a higher level of mathematics. When consistency is made possible and several conditions are satisfied, the results could be used to derive a large class of estimators.
Okay, so the law of large numbers was really proven by a named Jacob Bernoulli. He spent over 20 years working on this theorem, later publishing it in 1713 in his book titled Ars Conjectandi. Here it is in a Latin cover. More than a century later, we have other mathematicians refining it, as well as coining the term law of large numbers. Um, and here on the bottom, we see a quote from Bernoulli, um, really hammering home the intuition sense of this law, saying even the stupidest man, by some instinct of nature per se, and no previous instruction, knows for sure that the more observations that are taken, the less the danger of straying from the mark. All right, and this leads us up to today, where machine learning is one of the most popular topics built from this principle. This is mainly because of how machine learning is heavily influenced by data collection and data analysis. Best way to describe it is that you split your whole data set into 80% training and 20% test. And you hope that you give your training data set to the algorithm, and let's just say it's a categorizing one. The categorizing algorithm should treat the test data the same way it treated the training data, and we evaluated that. But if we consider that the larger the numbers of observations we give the training and testing sets, the more likely it is that our categorization algorithm is not only correct but effective.
Moving on from the concept, we have the theorem here. We know the sample mean definition, which is x bar equal to x1, x2, all the way to xn divided by n. We know that the sample mean is equal to mnx, which is a random variable and can be used to find the expected value of the sample mean in var x. Now, the weak law of large numbers states that if we let x1, x2, all the way to xn be random variables with a finite expected value, we know that the mu is less than infinity, then for any epsilon greater than 0, we have the limit shown below. Now we look at some examples of law of large numbers at work. We have the gambler's fallacy, which is that the probability for an outcome out of a series of outcomes is not the same as the probability for a single outcome. So the example here is if you toss a coin 5 times and they're all heads, well, you would think that, the probability of tails must be higher for the next one. But instead, the probabilities are all the same, which is 0.5. The law of large numbers only works when the number of trails approaches infinity. So we need 1,000,000 flips to have the 50-50 heads and tails. 5 trails does not work here. The next example is lottery tickets. There's some lottery ticket numbers that has never won a prize before, and people think that, that must be the winning number. However, each number has the same probability as the other numbers in this trial, and we don't have enough trails to show that each number would be the winning number.
Okay, so this is David, and I'm going to go over the proving process of the weak law of large numbers. And before proving, I'm going to introduce 2 new concepts. The first one is converging probability. Converging probability, assuming there's an infinite sequence of random variables, and there's a constant a, if for any given positive epsilon, the limit of this probability is 0. Now we call this sequence is convergent in probability at a, and here is the mathematical notation. So what is converging probability? Here is what a sequence of random variable looks like, and as the sequence becomes larger, on the probability of the element falling out of the interval a minus epsilon and a plus epsilon is nearly 0, and when n approaches infinity, the limit is 0. This means that mostly the elements will fall inside the interval. And another new concept is Chebyshev's inequality, and this is very similar to the previous one. If you learn about statistics, you'll probably know that the probability of an element falling out of the 2 sigma's boundary is only about 5%, which is very, very low. So Chebyshev's inequality describes the fact that most events will be concentrated near the average, the sample mean. So now we can prove the weak law of large numbers, assuming that the expected value and the variance are both exist, and we have this. So here we put the sample mean into this function, into this format, and then we take this 1 over n out and convert this variable of the sum of the sequence into this variance notation, and we get this. So note that the mean of the sequence is the mean of the sample average. Now we can use the Chebyshev's inequality, and we have this in the equation. And with the probability of the with the property of the probability, the sum of the total events is 1. So we have the inverse of the Chebyshev's inequality, 1 minus this. And as n approaches infinity, the expression approaches 1. So by the definition of convergence in probability, we have obtained this. This is the convergence in probability.
Perfect. So now that we've covered both the theorem and proof for law of large numbers, we can jump into the first problem. So let x be a random variable, which is the height in meters of a randomly selected Canadian, where the expected value is let's call it h. Now, suppose that no Canadian is taller than 3 meters, and let's assume standard deviation is 1.5 meters. So we're going to use big H to denote the average of the heights of these n randomly selected Canadians in our experiment. So in part A, we're just asked to determine the expected value and the standard deviation of h, which is pretty easy. So it's important to note that h is a random variable, right? So we're summing x1 plus x2 all the way through xn and dividing it by n, right, to represent the average. So using linearity of expectations, we see expected value of h is just the expected value, again, of the sum x1 through xn. So we can just pull out the n, and we'll see that these cancel. So we're left with just e sub x, which we know from the info on the last page is just h. As for the standard deviation of big H, we can rewrite that as the square root of the variance of h, which again can be rewritten as the square root of n times the variance of x over n squared. So let's simplify the n's again. We're left with the square root of n in the denominator, and we're left with the square root of variance of x in the numerator, which we know is just the standard deviation, which is 1.5. Now, let's go back to part B, and we can see that part B is asking for a minimum value of n such that the standard deviation of h will be less than 0.01 meters. So, right, we calculated a standard deviation in part A. So we just set 1.5 over the square root of n less than 1 over 100. And we'll see that n has to be greater than 22,500 trials. So that would be the minimum value. And then again, we can go back to part C, which is where it gets really interesting now. So now we have to use, we want to be 99% sure that our estimate is going to be within 0.05 meters of the true average height of Canadians. So we're going to use Chebyshev's inequality to find the minimum value of n such that we're satisfied. So let's take a look at how to do that. What we're going to do is we know that from Chebyshev's inequality that the probability of big H minus its expected value is less than epsilon. Here, where that very small number, we're setting it to 0.05. And that has to be greater than this entire expression that we see here. So what we're going to do is we're going to take this expression and set it greater than or equal to 0.99, right? Because we want to be 99% sure. And again, substitute the standard deviation, which we know is 1.5 over the square root of n. And then all I'm going to do is subtract 0.099 and move this to the other side. And then this right here will simplify into 900 over n, which we're saying is now less than or equal to 0.01. And then again, it's some really simple algebra just to see that n is going to have to be greater than or equal to 90,000. So we need at least 90,000 trials in order to be 99% confident.
Okay. Hello, I'm Anthony, and I will be presenting the practice exercise 2 for our project on the law of large numbers. We'll read the problem real quick. It's pretty simple. Suppose someone gives you a coin and claims that this coin is biased, that it lands on heads only 48% of the time. You decide to test the coin for yourself. If you want to be 95% confident that this coin is indeed biased, how many times must you flip the coin? Well, this is just the start for the solution. We let x be the random variable such that x is equal to 1 if the coin lands on heads and x equal to 0 if the coin lands on tails. This is, if you recall, is a binomial random variable. So of course, our mu, our expected value, is going to be 0.48 to represent the probability of the coin landing on heads. And then our variance here, again, using the variance that we get from binomial random variables, this is going to be the probability of the coin landing on heads multiplied by the probability of the coins landing on tails, which is going to be 0.48 times 0.52, which is equal to 0.2496. We're just going to, and then in the fashion of the law of large number problems, we're just going to test the coin by flipping it an arbitrary n amount of times, and we're going to allow for a 2% error of precision since we're going to be flipping it in so many arbitrary times. So We do all of this so that we can test the probability of the coin landing on heads being between about 0.46 to 0.5. Okay, so using the law of large numbers and Chebyshev's inequality from the previous exercise that we've seen, we want our n such that the probability of heads not being the expected probability or the probability of it being within our error of precision 0.02 is less than or equal to the variance of our binomial random variable divided by the amount of attempts multiplied by the error squared, right? Chebyshev's inequality right there. For our 90% confidence interval, we simply set our Chebyshev inequality equal to 0.05, since our on the left side for the inequality from before, that's going to be the probability, like we said before, that the coin lands on the probability of the coin landing on heads being within the 2% error precision. That's a mouthful. But we do some simple algebra and we get 0.2496, the variance, and then multiplied by 20,500 multiplied by 20 is equal to 12,480. So we're going to need at least 12,480 coin flips in order to solve this problem.
All right, well, that's it. Thank you so much for viewing our presentation on the law of large numbers.